Teardown time. This is the Cree 60 watt light bulb, a 2018 purchase. This one's quite interesting. It's good for enclosed fixtures, they claim. 22-year service life, 10-year warranty, high 90 plus color rendering index, California Title 20 compliant. Those are all kind of interesting things to see. Cree's moved away from manufacturing in the States, it looks like. This is a Chinese-made bulb. Let's see how it's built. So this is a classic shape, the endpoint of the LED market. If you looked at my YouTube videos of my channel from a number of years ago, there was a really incredible variation on how to construct an LED light bulb while the marketplace was still young. It's now that it's matured down to these inexpensive bulbs. They're all like this, it seems. A base, a emitter array, always planar, always this direction here, pointing into a dome, resulting in mostly, of course, in a downward firing light. Versus what actually happens in an incandescent bulb. You can see, of course, the LEDs here in yellow, the power leads coming up that are hand soldered on. Let's take these two screws out, maybe pry some more of the glue off, and take a look what's inside here. So as you can see, the electronics have now been pulled out of this base. It's really heavy, substantial metal heatsink here. I guess that's what allows the bulb to be used in enclosed light fixtures. It's hard to telegraph how heavy something is, of course, on a video, so I think I'll cut this apart and look at a cross-section of it, but there's a lot of metal there. Coming back to the base, you can see I've cut one in half. There's a fairly complicated casting here with a nice swoop on it. And then it looks like they overmold this plastic. It comes around here, then sharply turns around here and comes back up to the base here. I don't know if they could snap that on somehow. It's quite an interesting injection molded part otherwise, because it has an incredibly deep profile here. Anyways, the real key here though is a substantial amount of metal, providing the ability to take the heat from the LEDs and then get them down to the side here, where of course the heat can radiate away, and also get it down here so it can draw through the base and potentially have a path there for thermal conduction. So here's a close-up of the power supply AC input here, and then a high voltage DC which goes to the actual emitter. There's the first thing you see is a safety device. It's a fusible link or a fuse of some sort sitting under there. I've just taken it and cross-sectioned it and just sitting in some modeling plaster here so it doesn't roll away from me. And you can see the structure a little bit indistinct. Let me take this over to my macro photography jig and I'll take a good photograph. Now what we can see here, of course, is it's a coil of wire around a spindle, looks like ceramic of some sort, and then a metal case. So that's kind of interesting. It runs in through this EMI suppression device, the choke. Basically, as noise is generated with the bulb, you don't want to push back in the power line causing radio interference. So that's this component here. Looks like they use a little bit of elastic to hold this onto the circuit board. There's a couple of high voltage capacitors, and essentially you get a high voltage DC coming into this little controller IC. There's a transformer here, and of course a rectifying diode here, which of course then goes to the smoothing capacitor, the electrolytic. The actual controller IC, as you can see, is really quite tiny indeed. And I suspect that's where most of the smarts are in this bulb. So let's take that off the board and de-encapsulate it and look at the controller. So sitting on this lab slide is this little spec, and that's the actual integrated circuit that was inside the package. That's the controller IC, incredibly small. 0.67 by 0.65 millimeters. That's the smallest one I've ever torn down, I think. Now there's two things that really control the price of a component. That's the size of the silicon die in the package. And so clearly here we're seeing a very cost-optimized part. Now if we just go to the microscope, we can get a photomicrograph of the silicon die looking straight down. And we can see that there's probably a FET-like structure on the left. Now, there's no power transistor on the actual circuit board, so that means the power transistor must be on this silicon die. Doing some quick math, that 120 volts comes in as AC, gets converted to about 170 volts DC. It's a 10 watt bulb, so about 7 milliamps would have to be going through the FET transistor. So yeah, that's possible, even though it's a really small FET. That's absolutely within the possible range. On the right-hand side, of course, you can see the controller, the transistors and such. There's a metallization on the top, then there's a metallization below that, and then the actual semis. Let me just pick the zoomed-in portion of the chip. You can sort of see the three regions. So no surprise, a relatively complicated function. Definitely done on a very modern process node. So this is definitely a state-of-the-art controller. Transformer. This is the thing which allows the higher AC voltage to be converted down to a lower DC voltage. Let's also cross-section this component and take a look at how it is constructed. So this is the cross-section of the transformer, and I must admit it has me a bit baffled. Just pointing out there with the highlights, that's the yellow tape that wrapped around the coil. And then, of course, you can see a bundle of wires, of course, which is the coil, but a transformer should be two bundles of wires separated by some sort of tape or something for dielectric resistance, and all I can see is a single bundle of wires. So it does have 4 leads, this component, so it's not an inductor, which leads me to wonder if they have a transformer where the primary and secondary are only isolated by a layer of enamel in the wire, which doesn't seem right to me. So I don't know if anyone has a expertise in transformer construction, but this looks too inexpensive for my eye. I was expecting a different construction, but that is what the transformer looks like when I cross-section. Okay, this is a light flicker test, the bulb here. This is a solar cell, and of course if I turn the light on, the light shines onto it and of course generates a electric signal that we can study on the oscilloscope. So here we have an oscilloscope, and obviously it's quite dark because I've turned the lights off in my lab. The solar cell is registering 0 volts because there's of course no light shining upon it. But if I turn the bulb on, we'll see of course the signal rises up, quite a significant DC aspect to it. And then there's just some 120 hertz signal here. Now that's a very low flicker. If you want to zoom into it, you have to go to AC, get coupled mode, and change your time voltage base. But this is a very moderate, very modest amount of signal, 15 millivolts. So this bulb has probably imperceptible flicker. Light distribution pattern. Obviously the bulb, and I've got it so I can turn it on. And what happens is I place the bulb here in the center, and then I use my light meter to measure the light intensity in terms of lux at 10-degree increments. The larger the number here, the greater the light. So for example, I can see 668 lux going this direction here, 162 here. And that makes sense, of course, like this is just metal and obviously no light coming out of it. And what you can do is you plug all these numbers into Excel and you get a nice polar graph. Now this blue blotch tells me that this bulb basically puts most of its light going this way, so light comes out going this way. Now, an H-shaped bulb traditionally with the filaments used to push the light sideways, and then would hit the light shade and illuminate the room. So early LED bulbs are all very, very carefully designed, at least the expensive ones, to try to push light this way. Now, eventually the marketplace won out in terms of cost. It's much cheaper to build a bulb in this construction here. One downside is you get the light going this way. Now you can see there's like a lobes here. That's also, if I suspect when I rotate the bulb here, you would see patterns going here as well. So the packaging said it takes 10 watts. As you can see, it's handily beating that figure. And the power factor is almost unity, so there's obviously some sort of power factor correction in the bulb, which all are good attributes. Let's look at dimmability. I always start with this old dimmer that was predating LED bulbs by probably a good decade. Some LED bulbs had real troubles with some of the earlier, older dimmers. Now this bulb is just fine with it. It definitely dims, but there's a dead band, probably about half the turn of the dial. The bulb is just simply in this low state, but it certainly does work. Let's switch over to a dimmer that was explicitly designed for LED light bulbs. Here's a much newer style of dimmer, and it was meant for LED light bulbs, and the dimmability is quite a bit better. The range is quite a bit nicer with this kind of dimmer. You'll still see that today. These old dimmers, of course, were never designed for LEDs. This bulb admirably handles it, but a fair bit of dead band in there. With this newer style, you get better performance. So sometimes you have an LED which doesn't seem to dim well. It really is the dimmer which is at fault. So yeah, this is really quite lovely actually with this newer style. Well, there we go. That was a teardown of a very modern light bulb from Cree. Very inexpensive looking semiconductor there. Impressively so. LED light bulbs now are just dropping to an incredibly low sell price. This one is a little bit better than the very lowest cost ones with a nice looking heat sink for the enclosed usage. That definitely seems to be quite credible. High CRI for the light and such. If you want to look at more details of the photographs, especially the semiconductors, I have a copy of those on my blog, electronupdate.blogspot.com.